Now from today we will start the comparison of averages, which is another type of the statistical analysis. So in these statistical tests we are going to see that how we can compare the average values, how we can compare the mean values. So often we need a comparison of averages. In statistical analysis we need to compare the mean values. And the general question in this query or in this analysis is the observed difference between the average of two samples significant, or is it due to the chance sampling error? So this is a general question which is behind, which forms the basis of every test of comparison of averages, every test for the comparison of mean values. That is the observed difference between the average of two samples significant? So should we consider this difference as the significant difference, or is it due to the chance sampling error? So this is the main question that needs to be answered during this statistical analysis. So for that purpose, to answer this question, a test is needed to check the significance of a difference between the averages of two samples. And because we're talking about the statistical test, so we have to put down the hypothesis. So the general hypothesis for the comparison of averages are the null hypothesis first. So the null hypothesis, the general null hypothesis is samples are drawn from populations with identical averages, and any observed difference between the samples is due to sampling error. So this is the general null hypothesis, that the samples, they are drawn from populations with identical mean values, and the observed differences in the sample means, they are because of the sampling errors. So this is the null hypothesis. Then the two-tailed alternate hypothesis is that samples are taken from populations with different averages, and observed differences between the samples cannot be accounted for by sampling error. So in this alternate hypothesis, we are assuming the two populations to have different mean values. So we are not nominating any specific population to have the greater value of mean. Rather, we are just saying that these populations are with different averages, right? And the observed differences in the sample means, they are significant enough that they cannot be ignored to be accounted for by the sampling error alone. So this is the two-tailed alternate hypothesis. Then we have the one-tailed alternate hypothesis, and in the one-tailed alternate hypothesis we nominate a sample to have a larger mean value. So a nominated sample is drawn from a population with a larger average than that from which the other is drawn, right? So these are the hypotheses in general. Now, before we start the statistical procedure, there are some concepts and definitions that need to be discussed before starting the statistical analysis. And the first one of these concepts is the concept of matched and unmatched observations, right? So matched observations are taken from those samples in which the same variable is measured twice on each subject under different conditions or different times. So it means that the same variable, the variable that we are studying, the study variable, it is measured twice on each subject of the population under different conditions or different times. So what does it mean is that we are recording the same variable, but we are recording the same variable 2 times from each unit in the population. And why we are taking that 2 times from each subject? So there must be a change that we want to study the effect of, right? So we are taking these 2 measurements under different conditions or in different times, and we want to see the difference between the values between the variable of the same subject under these different conditions or under these different times. So these are commonly called as repeated measures. Why these are called as repeated measures? Because the observation is repeatedly measured, right? That is why this is known as the repeated measures test. And the example is masses of 10 birds on day 1 and masses of same 10 birds a week later. Then we have the unmatched observations, and the unmatched observations are those samples in which the same variable is measured from two groups of subjects. So in this case, we are not taking the repeated measures, rather we are taking the observations, we are taking the measurements only once of the same variable, but this time they are taken from two groups of subjects, right? So these populations, they are different from each other. For example, masses of 10 birds from one side and of another 10 birds from another side, right? So in the previous example, we saw that the masses of the 10 birds are measured on day 1, and masses of the same 10 birds are measured again a week later. And in this example, we are taking the masses of 10 birds from one side and of another 10 birds from another side. So in both cases, we have two groups, but in the matched observations, these two groups are matched, so these are paired observations. And in the other case, in which the unmatched observations are there, so in that unmatched observations, these birds are different. There are 10 birds from the other side and 10 birds from the other side, right? So this is a simple illustration in the form of table to understand the difference between the matched and the unmatched observation. So in the first table, as you can see, that the first column refers to the sample units. So there are 10 sample units, there are 10 birds, and these same 10 birds, they are measured twice for the same variable, sample A and sample B. So they are taken from the same sample units. And then in the unmatched observations, again we have 20 different observations. But these 20 observations, they are taken from two different populations, right? So in the sample A, we have 10 birds, and in the sample B, we have another 10 birds. So this is the difference between the matched and unmatched observations. Now we see some other example, like the month-wise number of hospital admissions in Islamabad in 2001. And if we want to compare them with the month-wise number of hospital admissions in Islamabad in 2019. Then another scenario, we take the month-wise number of hospital admissions in Islamabad in 2019, and we want to compare them with the month-wise number of hospital admissions in Peshawar in 2019. So now these are two different scenarios. So in the first scenario, we can see that the unit of sampling is same, right? The unit of sampling, unit of taking observation is same, but the observations are being taken on different times. So this one is the matched observation. And then in the second example, we can see that the same variable, the variable is the number of hospital admissions, so the same variable is being measured, but this is being measured from two different set of subjects or two different set of units, months in Islamabad and the month-wise distribution from Peshawar. So these are the unmatched observations that we have. Then we have another example, the condition factor of fish before and after eutrophication. So we have fish and we calculate their condition factor, and then eutrophication occurs in the cultures, and then we want to see that if there is a change in the condition factor of fish after eutrophication. So this will be the matched observation, because we are taking the sample of same fish before and after a condition. Plant root biomass is at different depths of the roots. So in this case also, two observations are taken, and these observations are being taken from the same sample unit. So these are being repeated, or these are paired. These are related to each other. And then the unmatched examples, the plant growth rate in response to salinity stress in two ecozones. So here we have two different populations, and these two populations we want to see that what is the plant growth rate in response to a salinity stress. So in this case, the observations are not repeated, the measurements are not repeated, rather they're taken from two different groups. So this is an unmatched observation. And then if we want to see the difference in cholesterol levels between females and males, So the variable is the cholesterol levels, and the study groups are females and males. So these are also unmatched observations. And now here is another concept that we need to study when we are studying the comparison of averages in statistics, and this one is the concept of normal distribution. Because most of the statistical analysis that we use for the comparison of mean values, they assume that the observations, they are normally distributed, right? So the comparison of averages assumes that observations are normally distributed, so they should follow a normal curve. Because a probability distribution specifies the probability of getting an observation in a particular range of values. So you remember the distribution of probability from a normal curve that we discussed in the previous lectures. So we can actually define the probability distribution by using the properties of normal curve, and we can actually get the probability of getting an observation in a particular range of values by seeing the properties of the normal curve. So the normal distribution is the familiar bell-shaped curve, and there is a high probability of getting an observation near the middle, and there is a lower probability away from the middle, right? So here we have a perfectly normal distribution, which is a perfect bell-shaped curve. So in this curve, you can see that the probability of getting a random value is very high, close to the middle of the curve. So most of the observations, they are scattered around the mean value, right? So this class, which is the 7th class, that represents the mean value, and most of the observations, they are scattered around this value. And as we move away from this center of the curve, the probability of getting a value gradually decreases until we reach the 1st class and the 13th class, where the probability of finding an observation is minimum, right? So that is why we use a normal distribution to compare the averages, or to compare the mean values in most of the statistical analyses. Now, in contrast to this, not in contrast to this, rather, there is another curve, there is another distribution which is not perfectly normal distribution, rather this is near normal distribution. So why we are considering this one as the near normal distribution? Because this is a unimodal data. You can see that there is only one peak, and in this distribution as well, the values, they are mainly centered in the middle, and as we go away from the middle, the probability of finding a value gradually decreases. So this is not a perfect normal curve, rather this is a near normal distribution, and this distribution can be used. So the comparison of averages test, they can be applied on this kind of distribution as well, because it is sometimes very hard to find a perfectly normal curve. So near normal distributions in which the distribution is unimodal, and the most of the observations, they are scattered around the middle value. So that kind of graph, or that kind of data, that can be used for the analysis of comparison of mean values. So now we see the contrasting type of the graphs. So these type of the graphs, these type of the histogram, so this shows a non-normal distribution. So this is a not normal distribution, and you can see that values are skewed to one side. So one side of the distribution, it has very few values, and the other side of the distribution has quite a large number of values, and this concentration is not in the middle of the curve, it is not in the middle of the distribution, rather this is only on one side. So this is not a normal distribution, so this is a non-normal distribution. Then we have another example of a non-normal distribution in which we can see no trend. So you can see that there is no trend, and you cannot identify the central value, that where the observations are scattered, and you cannot apply the rules of standard error and the rules of probability on this type of the distribution of observations. So normal distribution is a requirement for most of the tests which require the or which are used for the comparison of mean values. So our data should be normally distributed. So what if we have the data which is not normally distributed, right? So what should we do with that data? Should we leave that data, or should we find some other solution? So for that kind of the data which is not normally distributed, we can adopt different approaches. Like we can adopt the approach of data transformation. We can log transform the data. So log transformation, it often gives the normalization of the data, and the data which is scattered and which doesn't show any trend or which is skewed to one side, so that data can be near normally transformed by different methods, and the best method is the log transformation of the data. So you can log transform your data, and then you can apply the statistical analysis for the comparison of mean values. The other option is that you can apply some other test. So there are some tests that do not assume the distribution to be a normal distribution, the tests which are not that sensitive to the normal distribution. So those type of tests can be used. For example, the Wilcoxon signed rank test. So this test can be used for the comparison of averages if our data is not normally distributed. Then another attribute of the comparison of averages is the homogeneity of variances. So this is mainly the attribute of the unpaired sample t-test, or which are the unmatched sample t-test. So for that purpose, we need to assume that variances of the two samples are similar. So the general null hypothesis for this kind of the analysis of means is that two samples are drawn from populations with identical means and variances. So if the outcome of a test suggests the rejection of null hypothesis, then the possibility that it is due to difference in the variances should be eliminated. Because it is quite possible that if one of the samples, if one of the populations has a larger variance and the other population has a smaller variance, then it is quite possible that difference in their mean values is because of that difference in the variances. So therefore, we need to make sure first that the difference between the mean values is not because of the variances. So we need to check for homogeneity of variances between the two samples before we actually apply the t-test for unmatched observations. So the variation in sample means will be greater than the variation due to random differences among individuals. So we need to make sure that this is not the case. So what we can do to check the homogeneity of variances, we can apply a simple test, and that test is called the F-test, and F-test is basically the comparison of variances. So it is applied before applying a test for differences in mean, and if the result of this test suggests variances are not similar, then a test for difference between means cannot be applied. So this is a pre-test that we need to do before doing the t-test for the unmatched observations, and we need to make sure that variances are similar. There is homogeneity of variances, but if the variances are not similar, then we cannot perform the t-test for unmatched observations. So this simple test needs to be done first. So what is the F-test? There are different types of the F-tests, and the F-test that we use before the t-test for unmatched observation is the two-tailed F-test. So this test assumes that the two populations with identical variances, they have a variance ratio of unity that is equal to 1. So when we say that the two values are equal, so if we are going to divide one value by the other, the answer should be 1, because if both values are same, the answer should be unity. The answer should be 1. For example, if we have value of 3 and the other value is also 3, then 3 by 3 is 1. If we have one value as 5, the other value is also 5, then their ratio is 1. So departure of sample variances from unity, that if they are different from 1, then it is supposed that this is because of the sampling error, right? So this is assumed that this is because of the sampling error. So we need to check that whether this is because of the sampling error or whether this difference is significant. We need to apply the F-test. So this is tested through a variance ratio or F-test, and this is the null hypothesis, and the null hypothesis says that the population variances are similar. The ratio of the population variances from the two samples is equal to 1. And the alternate hypothesis, this is a two-tailed hypothesis, and it suggests that the variance ratio is not equal to 1. Variance ratio of the two populations is not equal to 1. So this is the null hypothesis and the alternate hypothesis for the two-tailed F-test. And this is the formula for the calculation of F-test, that the numerator in this formula is the greater variance, which we label as sample number 1, and the denominator is the lesser variance, the value of the sample which has the lesser variance. So that is sample number 2, and this is taken in denominator. So we take this ratio and we check that whether this ratio is significantly different from 1 or no. So this is a simple formula of t-test. The degree of freedom for the F-test, we have 2 degrees of freedom because we have 2 samples. So V1 is the degree of freedom for the sample number 1 or numerator, and V2 is the degree of freedom for sample number 2, which is denominator. So we calculate 2 degrees of freedom. So we are taking one example, the 2 samples of limpets which are collected randomly on either side of an island. And the variable which is measured from these samples of limpets is the maximum shell length. These are the descriptive statistics for this data. So we have sample number 1, which is the west side, and sample number 2, which is the east side. So the number of observations on the west side is 41, on the east side is 31. The mean shell length from the west side is 24.71 millimeters, and the mean shell length from the east side is 19.6 millimeters. And then we have the standard deviation, which is 6.34 millimeters for the west side and 4.82 millimeters for the east side. And then we have the variance values, which is 40.1956 for the sample number 1 from west side and 23.2324 for sample number 2 from east side. And the degrees of freedom are 41 minus 140 and 31 minus 130. And this is our simple analysis. So you see how quickly this can be done if you have the descriptive statistics with you. So F is 40.1956 in this case, divided by 23.234, because remember the F-test is the greater variance divided by the lesser variance. So greater variance in this case is 40 and the lesser variance in this case is 23. And when we divide that, the ratio is 1.73. So what should be the next step? To see if this calculated value is greater or less than the tabled value for the F-test. So here we have the F distribution table at the probability level of 0.05. So all of these observations, they are at the probability level of 0.05, and you can see that there is V1 and there is V2. So in the columns we have a V1 distributed, and in the rows we have V2 distributed. And these are 2 pages because there are a large number of values. So on the other page also we have V1 and V2. Right? So what was our V1? It was 40 in this case, and what was our V2? It was 30. So our table value is 1.79, right? So we have our calculated value, which is 1.73, and we have our table value at probability 0.05, which is 1.79. So which one is greater? Our table value is greater. So our calculated value is less than the table value, therefore we are going to accept the null hypothesis. And the null hypothesis is that 2 samples have been drawn from 2 populations with equal or very similar variances. So this is the F-test that we do. So after we are done with the F-test, we may now proceed for a test for a significant difference in the mean values. So this is a pre-test that should be done before doing the t-test for unmatched observations. So if we accept the null hypothesis in this case, which means that variances are non-significantly different from each other, then we can proceed for the actual analysis of the difference in the mean values. So we have another example for the F-test calculation. This is the dry weight in milligrams of leaves, and these are from two different fields, sample 1 and sample 2. So in the first field, the number of observations are 76. In the second field, the number of observations are 61. The mean dry weight of leaves is 84.33 milligrams from field 1 and 69.45 milligrams from field 2. And then we have the standard deviation, which is 5.84 milligrams from field 1 and 4.53 milligrams for field 2. And then the variance value, which is 34.55 milligrams from field 1 and 19.13 milligrams from field 2. So which one of these variances is greater? The variance from sample number 1, therefore we have labeled this sample as the sample number 1. And then we have the degrees of freedom, which is 75 for sample 1 and 60 for sample number 2. And then we do our calculation for the F test, which is 34.55 divided by 19.13, and we get our ratio as 1.8061. So this is our calculated value of the F test. Now consulting the F distribution table, our V1 is 75 and our V2 is 60, so our table value is 1.51. Now we compare the table and the calculated value. The table calculated value is 1.8 and the table value at probability 0.05 is 1.51. So here in this case, our calculated value is greater than the tabled value. So what do we do with the null hypothesis? We accept it or reject it. So obviously we are going to reject the null hypothesis because the probability of null hypothesis to be true is less than 0.05. So therefore we are going to reject the null hypothesis, and we can say that two samples have been drawn from two populations with significantly unequal variances. So variances are significantly unequal, and these variances, they are not because of sampling error, rather rather they actually exist at the level of population. So because our variances are not same, our variance ratio is not equal to unity, so we should not proceed to test for a significant difference in the mean values. And now I want to show you an online calculator for the F critical value or the table value of F, and this is a web link for that online calculator, and this is how it looks like. So when you go into this web link, you'll find this calculator. So this calculator will tell you the critical value of the F distribution given the probability level, the numerator degrees of freedom, and the denominator degrees of freedom. So you just have to enter your necessary values and then click calculate. So we have these three boxes, so we have to fill these three boxes. So now the first input for V1, which is the degree of freedom of sample number 1, which is our numerator. So in the box 1, we are going to put in the value of V1. Then in the next box, we are going to put in the value of V2, which is the degree of freedom of sample number 2, and this is the denominator. And remember, the sample number 2 or the denominator is the sample which has lesser variance. So this should be put in box number 2 of this calculator. Now we are going to put the desired level of probability, and it should not be greater than 0.05. So in box number 3, we are going to put in our desired level of probability, and because we are applying this F-test to only check that whether the variances of the two populations that we are studying, that whether those variances are similar or no. So that is why we are just going to take the basic critical probability level, which is 0.05. So we cannot take the critical probability value greater than 0.05. So we are going to take the probability value of 0.05 against which we need to check our values, or we need to get the value of F distribution. So we are going to put 0.05 here. And now enter the values of V1, V2 and probability levels. For example, the degrees of freedom for sample number 1, 3, degree of freedom for sample number 2 is 5, and the probability level is 0.05. Now we press calculate and we get our results. So our result in this case 5.40945132, which is the table value of F for the degree of freedom V1 3 and degree of freedom V2 5 and probability level of 0.05. Right, so this is the table value of F, or the critical value of F at these degrees of freedom and probability level. And now we are entering the values from the example that we studied, and we studied the example of the shell length of limpets. So we are putting in the values. So what was our V1 in that example? V1 was 40, and what was our V2? V2 was 30, and the probability level against which we checked was 0.05. So when we enter these values, what do we? So we get 1.79, and you can see that this is exactly the same value that we got from the F distribution table, right? So this is the value that we obtained. Now we put the values of the second example that we used. We used the example of the dry weight of leaves taken from 2 different fields. And what were our V1, V2 and the probability level? So our V1, the degree of freedom of the sample with greater variance, was 75, and V2, which is the degree of freedom for the sample with lesser variance, was 60. The probability level against which we are checking is 0.05, and when we calculate, we get the result, which is 1.50850109, and this is 1.51. And again, you can see that this is exactly the same value that we got from the table. So this is all for today's lecture, and in today's lecture we are starting the another series of the statistical analysis or statistical test, and this time we are focusing on the comparison of mean values, the comparison of averages. And we saw the general hypothesis for these kind of the tests. And what is the general hypothesis? General null hypothesis is that the samples have been drawn from populations with identical means. And the two-tailed alternate hypothesis is that the samples are drawn from populations with significantly different mean values. And the one-tailed alternate hypothesis is that in which we nominate one of the samples to have the greater value of mean as compared to the other sample. And then we saw some concepts and definitions, like we saw the concept of the matched and unmatched observations. So the matched observations are those in which the samples or the observations, they are taken from the same set of sample units, and the observations are taken twice and under different conditions or under different times. So these are the repeated measures. And then we saw the unmatched test. Unmatched tests are those in which the same variable is measured, that the similar type of the variable is measured from 2 different populations, from 2 different groups, and these 2 groups, they are unrelated to each other, and the observations, the sample units in these 2 groups, they are unrelated to each other. So they are not taken from the same samples. And then we saw that why it is important to have a test of homogeneity. But before that, we saw that the normal distribution, that it is a basic assumption of most of the tests which are used for the comparison of averages, that our data should be normally distributed. So we should have the normally distributed data so that we can have an accurate p-value, probability value. And then in the end, we saw that the homogeneity of variances is a requirement of the unmatched t-test, which is the test for the comparison of mean values in the unmatched observations. and this is checked through a simple test which is called as the F-test, which is the variance ratio in which the greater variance is divided by the lesser variance, and then we compare the calculated value with the tabled value with the critical value, and there we can see that if the variances of the two populations, they are significantly different from each other, or they are not significantly different from each other. So if they are similar, or if they are non-significantly different from each other, then we can proceed for the t-test for unmatched observations. But if they are not statistically similar to each other, then we should not proceed for the t-test for the comparison of averages. So this is all for today.